Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 2.5, and here in 2.5, we'll be discussing infinite limits. All right, so here we go. So let's begin by letting f of x be equal to 1 over x plus 1. All right, now this is what that function looks like. We have a vertical asymptote here at x equals -1, and the function looks like this. We also have a horizontal asymptote here of 0. But so this is y equals 0. All right, but in here we're really concerned about what's going on here near the vertical asymptote. All right. Um, the question here really is, well, we know that the domain is that x can't be equal to not 0. X can't be equal to -1, right? That's the domain right off the bat. But the question is, well, what's happening at -1? So we want to see, well, what is the limit as x goes to -1 of f of x, right? But in here, we know that we can't plug it in, so this actually right away does not exist, all right? But now that we know about one-sided limits, all right, well, we can talk about, well, what's actually happening as we're approaching -1 from the left of the function, and also what is happening as we're approaching -1 from the right of our function. All right, so from the left, we're going down to -infinity. From the right, we're also going up to +infinity. Now, normally when we talk about our limits being infinity, we still say does not exist, but we want to be able to still know whether it's actually in a negative infinity way or a positive infinity way, because that's going to help us find out some behavior of these functions. All right. Similarly, let's look at another function. Let's say that I had f of x is equal to 1 over x minus 2 quantity squared. All right. Now this function looks as follows. It's got a horizontal asymptote here so that's a horizontal asymptote of y equals 0, and it's got a vertical, no, that's not where it is. That's not where the vertical asymptote is. It's over here at 2. So this is our vertical asymptote of x equals 2. All right, so now um, we know that this function, oh, hold on, let me draw the function. So this is what it looks like. All right, that's what that looks like. So in here, again, we want to be able to find out what this behavior is around this asymptote. All right, we know that the domain is that x cannot be equal to 2. So we want to find out what's happening near there. And we already know that that's an asymptote. So let's figure it out um, algebraically why this would be going to positive infinity. So we have the limit as x goes to 2 from the right of our function. We're going to say that's positive infinity. And the limit as x goes to 2 from the left of our function, that's also going to be positive infinity. So overall, what we see here is that this is really, overall, we can say that the limit as x approaches 2 of our function is infinity. But again, this really means does not exist, right? But again, even though it does not exist, doesn't mean it's not valuable to us to know that it is a positive infinity, okay? Um, so in general, whenever we know that there's going to be an asymptote, we we want to know what's actually going on around that asymptote. All right, we want to figure out whether it's going to go up to positive infinity or negative infinity. In fact, that is the very definition of a vertical asymptote. So let's define it. Vertical asymptotes. All right, so if the limit as x goes to c from the left of f of x equals positive infinity, plus or minus infinity, or if the limit as x approaches c from the right of our function goes to positive or negative infinity, then the line x equals c is a vertical asymptote of f. All right, and that's a vertical asymptote. Um, so, and again, what we really care about here with these vertical asymptotes is what is the behavior? Is it going towards positive infinity or negative infinity? Okay. So now, theorem. And this theorem says this is for vertical asymptotes. Vertical asymptotes. And it says let f and g be continuous functions. So be continuous on some open interval. On an open, that's how you spell open. On an open interval. All right. If f of c does not equal 0, but g of c is equal to 0, and there exists an open interval containing c such that g of x is not equal to 0 for all x not equal to c in the interval, then the graph of f of x over g of x has, so hold on, maybe I'll define that to be a new function here. So the graph of h of x, where h of x is f of x over g of x, has a vertical asymptote, at x equals c. So essentially, if the value of c makes the denominator 0, but it does not make the numerator 0, then at that point you're going to have a vertical asymptote. So here we go. Let's do some examples. So in here we're going to say find the behavior of each asymptote. And by here I'm talking about the left hand and the right hand behavior, all right, of each asymptote from either side. Right. All right. So let's look at the first example. So example A. It says f of x is equal to 1 over 7 of x minus 1. Or 7 times x minus 1. All right. So in here, well, we know how to find our domains, right? And what we want to figure out here is, well, first of all, what is the domain? And the domain is that x cannot be equal to 1. Now, let's think about that 1. x can't be equal to 1 there because it would make the denominator 0, right? We end up with 1 minus 1 is 0 times 7 is 0. But the numerator, it remains unchanged with that, right? It doesn't matter what x is, the numerator remains unchanged. So what we're going to say here is that f of x is going to have a vertical asymptote at x equals 1. So vertical asymptote is x equals 1 because, again, that value made the denominator 0, but not the numerator. But now that we know that, well, we want to figure out the behavior from either side. So let's look at from the left. So we're going to say the limit as x goes to 1 from the left of 1 over 7 times x minus 1. And we're also going to look at it from the right. The limit as x goes to 1 from the right of 1 over 7 times x minus 1. Now here's the thing about vertical asymptotes, all right? And let me scroll up for a second. And here in this definition, we know that if it's going to be a vertical asymptote, well, that's because the limit went to positive or negative infinity, right? It's the only way it's going to be a vertical asymptote. So in here, essentially between that definition and this theorem, well, this tells us that these limits are going to go to some sort of infinity. The question is it going to go to positive infinity or negative infinity? All right, that's the question here. All right, because we know that at 1, we've got a vertical asymptote, but we need to figure out what's going on. It's got to go to some infinity. Is it positive or negative? Well, how do we do it? Well, here, notice that we're doing 1 from the left. All right, and since we're on the left of 1, well, let's look at 1. We want to plug in essentially a small value to the left of 1, something that's very close to it. For example, 0.9. Right? And that's essentially what we're going to be working with. That's 0.9. But we don't actually care about the outcome of plugging in 0.9. We just care about the behavior, right? So we just care about if it's going to make this entire thing positive or negative. Well, let's think about this. So we have on top, 1 is positive. On the bottom, 7 is positive. On x minus 1, if we're coming from the left, so plug it in something like 0.9. 0.9 minus 1, that's negative. So overall, this is, well, these two positives are just one positive together, right? Overall here, because I have one negative, this is going to go to a negative value. Specifically, negative infinity, because we knew it was going to be a vertical asymptote, all right? So we know that this goes to negative infinity. Similarly, well, let's look at this one. The 1 is a positive. The 7 is still positive. That x minus 1, but we're on the right of 1 now, right? We're coming from the right. So think about, well, what if that was like 1.1? 1.1 minus 1 is a positive number. Overall here, these are all positive, so we end up with positive infinity. Now, what did we find here? Well, it turns out that, that this function looks like this. So it has a vertical asymptote at x equals 1, and it does this. Notice that these one-sided behaviors essentially told us that we've got this positive infinity on the right, right? On the right, it went to positive infinity, and on the left, it went to negative infinity on the left. All right. So that's really what these one-sided limits are super useful for when it comes to asymptotes, to vertical asymptotes. All right. So that was A. B. Let's say that I had something like f of x is equal to x squared plus 1 over x squared minus 1. All right. And I'm just going to go ahead and rewrite this now as x squared plus 1 over this bottom factors out to be x plus 1 times x minus 1 because that is the difference of squares. So in here, my domain is that x cannot be equal to 1 or negative 1, right? It cannot be equal to either one of those. Maybe I'll write them in increasing order. It cannot be -1 or 1. All right, way better. Now, in here, well, let's see what happens when we plug these into the top. When I plug in -1 to the top, I end up with 2. When I plug in 1 on the top, I also end up with 2, right? So in here, well, those values of 1 and -1, they do make the denominator 0, but not the numerator. So that means that we're going to have vertical asymptotes at x equals -1 and at x equals 1. So what we need to do now here is we want to classify, well, we want to figure out what's going on around those asymptotes, all right? We want to see if they're going to positive infinity or negative infinity. So let's see. Let's start with -1. So for x equals -1. So we're going to take the limit as x approaches -1 from the left of our function. So we had x squared plus 1 over x plus 1 times x minus 1, right? And we're all going to do that also with going to -1 from the right of x squared plus 1 over x plus 1 times x minus 1. All right, now recall that here we're going to get some sort of infinity because we know that they are asymptotes. So let's look at our number line, all right? So we have -1 and 1. So we're approaching it from the left of -1. So something very close to the left of -1 would be -1.1, right? That's to the left of -1. So let's see what happens here. And again, all we care about is the overall behavior. Now let's look at the numerator, all right? The numerator, we've got x squared plus 1. It doesn't matter what we plug in for x there because we're going to be squaring it. And when we square it, it's going to be a positive value. And then that positive value plus 1 is going to be even a bigger positive value. So overall, the numerator is just positive. All right. So the numerator is always just positive. Now on the bottom, let's see what happens. I plug in -1.1. -1.1 plus 1, that's negative. -1.1 minus 1, still negative. So overall here, well, negative times a negative is positive. So I have positive over positive, which gives us positive infinity. On the bottom, on the next one, x squared plus 1. Again, for the same reasons, the numerator is just positive. But now let's plug in something to the right of -1. So something to the right of -1 is something like 0.9. All right. So in here, well, what does this give us? We've got on the bottom here, -0.9 plus 1. Well, that's positive. -0.9 minus 1. That's negative. So overall here, well, I've got a positive over a positive and negative. Overall, this goes to negative infinity. All right. In general, whenever we have these, we can just count how many negatives we have. And if we have an odd number of negatives, then the answer is going to be negative. But if we have an even number of negatives, then the answer is going to be positive. All right. So that was around x equals -1. But we also need to do it around x equals 1. And also we're going to do it just like before with from the left. So the limit as x approaches +1 from the left. And also the limit as x approaches +1 from the right. And we're doing this of x squared plus 1 over x plus 1 times x minus 1. All right. Now in here, well, let's see what we have. We're going to take the limit of 1 from the left. 1 from the left, that's something like 0.9. So on the top, again, we said the top is just always going to be positive because we're squaring and then adding 1. But on the bottom, 0.9 plus 1, that's positive. 0.9 minus 1, that's negative. So overall here, well, how many negatives do I have? 1. That's an odd number of negatives, so it stays negative. On the next one here, well, something to the right of 1, to the right of 1 would be something like 1.1. All right. So in there, the numerator is positive. 1.1 plus 1 is positive. 1.1 minus 1 is positive. Here, everything here is positive, so we end up going to positive infinity. All right, and essentially what this tells us is that the graph will look something like this. All right, we're gonna have vertical asymptotes at -1 and at 1. All right, and from the left of -1 it's gonna go to negative infinity. From the right of -1 is gonna go to positive infinity. From the from the left of 1 it's going down to negative infinity, and from the right of 1 it's going up to positive infinity. All right, so that's what we end up with on that. Um, all right, right. So the left of 1 negative infinity, the right of 1 positive, left. Oh, I messed this one up. Left is positive infinity. Look at that. So I messed this up. So left is positive infinity, and perhaps I should have been doing these with a different color so it doesn't get blended in with that blue. All right, so let's do that part again. From the left of -1, we're going to positive infinity. From the left, going to positive infinity. From the right, we're going to negative infinity. From the left of 1, we're going to negative infinity. And from the right of 1, we're going to positive infinity. So there we go. And in fact, this function looks something like this. All right, it looks like this. Something very similar to that. Yeah, I think the bottom one's a little bit lower because that kind of looked like it was hitting the x-axis. I don't think it does. But again, the idea here was just the behavior near those. Let's look at a similar example. So that was B. C. So let's say that I have f of x being equal to x plus 1 over x squared minus 1. All right, so here we go. The very first thing I'm going to do here is I'm going to factor out the denominator. So I have really x plus 1 times x minus 1. So right away, I know that my domain is x cannot be equal to -1 and x cannot be equal to positive 1. But notice here that I could rewrite this now as 1 over x minus 1. Ooh, so, but that is as long as x is not equal to positive 1. Now, what does that, to -1. Negative 1. Now, what does this actually imply about this domain? Recall that these values are where we're going to have discontinuities. This is essentially telling us that at x equals -1, this is a removable discontinuity. All right, because we were able to cancel that out. And it also tells us that this x equals 1, that's going to be our vertical asymptote. So at x equals 1. All right, so again in here, since we were able to cancel out that x plus 1 that was on the denominator, that tells us that at x equals -1, we're going to have a removable discontinuity. But over here, when I plug in that 1 on the bottom, I get 0 on the bottom, but not on top. That's another way that you can think about this, right? If I plug in -1, right? If I plugged in -1 into the bottom, I get 0. If I plugged it into the top, I also get 0. But our theorem up here said that when we plugged in into the top, right, f of x was the top, when we plug it into the top, we cannot get 0. It's only when we plug it into the bottom that we get 0 for this theorem to work like that, all right? So that's another way to think about why that would be a removable discontinuity versus a vertical asymptote. Now, now that we have that, well, we still have to figure out what's going on around these. All right. So first, let's figure out the stuff with the asymptote. Then we'll talk about this removable discontinuity. But with this asymptote, well, what we get here, we gotta figure out the stuff what's going around it. Um, from both sides. So we have the limit. Hold on, let me rewrite that. Here we're going to start with just the limit as x goes to 1 from the, well, let's start with the left of our function, which was, I'm going to use a simplified version, 1 over x minus 1. And then the limit as x goes to 1 from the right of the simplified version. All right. Now, we already know that around 1, we're going to have a vertical asymptote. So we know that these are going to go to either positive or negative infinity. All right. The question is, which one is it, positive or negative? So since we're working around 1, all right, so let's look at our number line. So again, here's 1, right? We're approaching it from the left, so something slightly smaller, something like 0.9. If I plug in 0.9, well, that numerator 1 is just positive. The denominator 0.9, 0.9 minus 1, it's negative. So overall, this goes to negative infinity. On the second one, we're approaching it from the right. So something like 1.1, right? That's on the right of 1. So if the top is just positive, right? But if I plug in 1.1 on the bottom, 1.1 minus 1, that is a positive value. So overall, this is a positive infinity, all right? And again, we already knew that it went to some sort of infinity. So that's what happens around that vertical asymptote. But now, let's see about that removable discontinuity, all right? What we want to figure out here is, well, what is going to be, where is that going to actually happen? Now, we know that the x value is -1, but what we care about is what would the y value be? So what we actually do here is we take the limit as x goes to -1. I wrote that wrong. As x goes to -1, there we go, of our function x plus 1 over x squared minus 1. But we know, and it doesn't matter if it's from the left or from the right. All right, if it's going to be a removable discontinuity, this limit must exist, and not just the one-sided limit, but the limit overall. So in here, well, we know that this is just the limit as x approaches -1 of x plus 1 over x plus 1 times x minus 1, right? And that's how we know that this was a negative. That's how we know this was a removable discontinuity. So now I'm approaching -1, and we have 1 over x minus 1. And as we go to -1, well, what does this happen? Well, there's nothing wrong with plugging in -1 now. So -1 minus 1 is -2, so I end up with 1 over -2. So graphically speaking, what do we find with all these limits? So this is what we found. All right. Well, we know that there was a vertical asymptote at 1. So I'll do that like this. All right. It's a vertical asymptote. What we also find out here is that, well, from the left, it went to negative infinity, and from the right, it went to positive infinity. So from the left, it goes down here. From the right, it goes up there. What else did we find? Well, we also found that when we plug in, well, as we're approaching -1, so let's say that here's -1. As we're approaching -1, our y value is -1/2. But there's going to be a hole there because it's a removable discontinuity. So essentially, what we found here is where the height of that hole is. As far as what the rest of this function looks like, well, essentially it looks like this. All right. And that's where that hole ends up being. So again, this last limit was just to find where the hole was. The first two limits was to find the behavior around the asymptote. All right. Now let's look at some other examples. So that was example C. So let's look at this next one, example D. So let's say here that we had the following function, and we're going to kick it up a notch. F of x is equal to 4x squared plus 4x minus 24 over x to the fourth minus 2x cubed minus 9x squared plus 18x. All right, so what we want to do here first is we want to factor this because as written, that is awful. All right, that is an awful thing to try to work with. So let's factor this as much as possible. Now, how do we factor this? Well, the numerator, I see, well, let's just factor these two separately. If I have 4x squared plus 4x minus 24, well, they all have a 4, so I can factor out a 4. I'm left with x squared plus x minus 6, and that factors out to be, well, x plus 3 times x minus 2. Cool. Now, the denominator. Let's see what happens there. So we have x to the fourth minus 2x cubed minus 9x squared plus 18x. Well, let's do this one step at a time. I see that everything here has an x. So I can factor out an x. And I'm left with x cubed minus 2x squared minus 9x plus 18. The next thing I'm going to do here is I'm going to factor by grouping. All right, I'm going to see what we can do about factoring by grouping here. And I'm going to group these first two together and those last two together. So from the first two, what we can do here is I can take out an x squared, and I'm left with x minus 2. From the second two, I can take out a negative 9, and I'm left with x minus 2. Right? And at that point, well, I can say that this becomes, well, x times x squared minus 9 times x minus 2. But that x squared minus 9 can actually be factored out even more. So I have x times x plus 3 times x minus 3 and then times x minus 2. So what we really found out here is that this function can be rewritten so far as 4 times x plus 3 times x minus 2 over x times x plus 3 times x minus 3 times x minus 2. All right, so there you go. Now, what do we do next? Well, in here, notice that some of these things essentially cancel each other out. And what we're left with here is just 4 over x times x minus 3, as long as x does not equal to negative 3 or x does not equal to 2. All right. So now let's see what we found so far. The domain for this function is x cannot be equal to 0, x cannot be equal to negative 3, x cannot be equal to 3, and x cannot be equal to 2. But now, from these, well, some of these are asymptotes and some of these are removable discontinuities. The ones that we cancel out here, those are going to be removable discontinuities. So we cancel out the x plus 3, so that's that x equals negative 3. So in here, this is a removable discontinuity. All right. The other one that we canceled out was x minus 2, so that's for this one, x not equals 2. This is also a removable discontinuity. All right. Similarly, we can look at the other ones. Well, the ones that are left at 0, well, 0 would make the denominator 0, but not the numerator. Similarly, 3 would make the denominator 0, but not the numerator. So we can say very confidently that those are vertical asymptotes. All right. So at that point, now we need to figure out what's going on around all of these. All right. So perhaps I'll do the removable discontinuities this time first. So I'll do them in yellow. So we're going to say the limit as x approaches negative 3 of our function. And I'll just do the reduced version, which is 4 over x times x minus 3. 4 over x times x minus 3. All right. And in here, well, there's nothing wrong with plugging in that negative 3. So we have 4 over negative 3 times, well, negative 3 minus 3, that's negative 6. This becomes 4 over 18, which reduces to 2 over 9, right? Negative times a negative is a positive. All right, cool. Now, so that means that at the x value of negative 3, the whole is going to be at a height of 2/9. Similarly, if I take the limit as x goes to positive 2 of 4 over x times x minus 3, all right, and again, we're allowed to do this because this is the reduced version. Well, we end up with 4 over 2 times negative 1, right? 2 minus 3 is negative 1. So in here, 4 over negative 2 is negative 2. So again, what this tells us is that there's going to be a hole where the x value is 2, but the y value is negative 2. Now let's look at our asymptotes here. All right, so we had an asymptote at 0. So let's start with that. So around x equals 0. All right, and here's 0. I'm just going to put it to the left. We're going to look at something like negative 0.1, and to the right, something like positive 0.1. All right, so let's do this. So we have the limit as x goes to 0 from the left of, and again, I'll just do the reduced version for both of these. And because we already know that this is an asymptote, all we care about is it going to be going to positive infinity or negative infinity? All right. Again, it being a vertical asymptote already tells us that it's going to be some sort of infinity. So now, let's look at what happens when I plug in something from the left. And again, all we care about is the sign. On top, I've got a 4. That's positive. So it's only going to stay positive. X, well, I'm coming from the left, so negative 0.1. So this part is negative. Negative 0.1 minus 3. That's even more negative. There's an even number of negatives here, so that's going to go to positive infinity. Similarly, here this is positive on the bottom. 0 from the right, something 0.1, right? So 0.1, that's positive. 0.1 minus 3, that's negative. There's an odd number of negatives here, so this goes to negative infinity. Now let's look at what happens around the other discontinuity, the other asymptote, I mean, x equals 3. It is a discontinuity, but I meant to say asymptote. And in here, if this is 3, we're looking at things like 2.9 from the left and 3.1 on the right. All right. Let me put that 3 up here instead. All right. So if I take the limit as x approaches 3 from the left of, and again, we're going to do the reduced version. Well, what do we get? I'll just set up the other one too. 3 from the right. Now, as far as the numerator goes, well, we know that that 4 is just a positive value. So the numerator is just positive. On the bottom, plug in 2.9. Well, this is just x, so 2.9 is positive. Plug in 2.9, 2.9 minus 3, that's negative. There's an odd number of negatives here, so this just goes to negative infinity. Similarly, 3 from the right, well, plug in something like 3.1. The numerator, again, 4 is just positive. Plugging in 3.1 for x, that's a positive value. 3.1 minus 3, that's a positive value. Overall, there's no negatives here, so this is just going to positive infinity. All right. So graphically speaking, we found 2 holes and we found the behavior around 2 of our asymptotes. All right, so I'll just draw a generic idea of what we just found there. I'm not going to draw the actual function, just the behaviors that we found. So here is, that's not where I meant to do it. So here's at 0, right? So here is our asymptote. That's one vertical asymptote. And to the left of that, we're going to positive infinity. To the right of that, we're going to negative infinity. Then we had another asymptote at 3. So let's say here's 3. And to the left of that, we went to negative infinity. to the right of that, we went to positive infinity. And then what else do we have? We have removable discontinuities, which essentially are holes. So at -3, 2/9. So let's say that we have here a hole where the coordinate is -3, 2/9, and the other hole is at 2 with a height of -2. All right, so here this is at -3. Let's say this is 2 and this height of -2. So the coordinate here is 2, -2. So this function essentially looks like this. All right, something like that. All right. All right. Let's do another one. So that was example what? D? I think, yeah, D. So E. And this one says f of x is equal to e to the -2x over x minus 1. Let's do x minus 7, just to vary it up a little bit. We've had a lot of ones in these examples. So all right, so here we go. The very first thing I'm going to do here is I'm going to rewrite this as 1 over e to the 2x times x minus 7. All right, and to find the domain, we would say, well, that's where the denominator can't be equal to 0. So e to the 2x times x minus 7 cannot be equal to 0. So I've got the product of two things here. So either the first one can't be equal to 0 and the next one cannot be equal to 0. In this equation over here, we end up with x cannot be equal to 7. In this one over here, well, exponentials are never 0, so this has no solution. So we completely ignore that and we say, well, this is our domain. X cannot be equal to 7. Now, at this point we say, well, we need to figure out what's going on around there. Is this going to be a vertical asymptote or is it a removable discontinuity? Well, notice that if you plug in 7, right? If you were to plug in 7, the numerator is still not 0, but the denominator is now 0, right? Because we have here this 7 minus 7, so that would give us 0 at the bottom. So that is going to be a vertical asymptote. All right, so because it's a vertical asymptote, what we need to figure out now is what's going around it. So let's say if the limit as x approaches 7 from the right, so that's what we're going to do. And we have 1 over e to the 2x times x minus 7. And also the limit as x approaches 7, I think I said right before I meant left, of 1 over e to the 2x of x minus 7. And this one is from the right. So we're looking at the number line here, 7. So something like 6.9 and 7.1, all right, from the left and the right. So let's see what we get here. E to the 2x. E to the 2x is always positive, all right? Exponentials overall are always positive, irrelevant of what that exponent is. There might be a number in front here that might make it negative, but as it is, e to a power is just positive. So we're plugging in something from the left, something like 6.9. 6.9 minus 7, that's negative. So overall, this is going to go to negative infinity. Similarly, if I plug in something like 7.1, again, oh, by the way, 1 is positive, so the numerator is positive. So I'm plugging in something like 7.1. E to any power is positive. 7.1 minus 7 is positive. So overall, this is going to positive infinity. So I won't give the full sketch of this one, but I will tell you essentially what's going on around these asymptotes. So we have here is 7, and from the left, we went to negative infinity. From the right, we went to positive infinity. So that's the behavior that we found there. All right. All right. That'll be the end of this video. Since this is the well, actually, there are a couple of properties that I should mention before I actually end this video. So these are some properties of infinite limits. And I don't want to write in yellow. So properties of infinite limits. So let C and L be real numbers, and let F and G, well, F and G be functions such that the limit as x approaches C of f of x is positive infinity, and the limit as x approaches C of g of x is L. Alright, so these are essentially arithmetic properties of infinite limits. So if I have the limit as x approaches C of f of x plus or minus g, well, plus or minus g of x, well, we know that the limit of f of x is infinity, so we have infinity plus or minus L. L is some specific number. Infinity plus a number is still infinity. Infinity minus a number is still infinity, so overall, this stays as infinity. All right. 2. If I have the limit as x approaches C of f of x times g of x, well, in here, the limit as x approaches C of f of x, that's infinity, and the limit of g of x as x approaches C, that's L. Well, this has a positive, a possible couple of different solutions. So there's three possible answers here. If L is greater than 0, well then that limit is, so how would I say that? So actually let's write it this way. So this is going to be equal to infinity, where L is greater than 0. It's going to be equal to negative infinity if L is less than 0, right? So if L is positive, a positive number times infinity is positive infinity. If L is negative, a negative number times infinity is negative infinity. But if L equals 0, then this is indeterminate. And that says indeterminate. Let's actually make more space for it. So this is going to be indeterminate when L is equal to 0. All right, so those are the three options there. 3. If we have the limit of the quotient, so the limit as x approaches C, not 0, C of g of x over f of x. Well, this is going to be L over infinity, all right? And L over infinity goes to 0, all right? L over infinity goes to 0 because it's a specific number divided by a huge number. If I have the limit as x approaches C of f of x over g of x, well, I end up with infinity over L. And again, here I've got two possible solutions. All right, actually three possible solutions. So infinity over L. This is going to be positive infinity if L is greater than 0. This is going to be negative infinity if L is less than 0. And this is going to be indeterminate when L equals 0. All right. So those are the three scenarios there. And again, these are just general rules of or general properties of infinite limits when you have arithmetic combinations of functions. All right. Um, and 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 these properties should be used when you're looking for to simplify any of these kinds of limits. All right, and you end up with an infinity somewhere in there. Well, make sure you treat it correctly that way. Um, that's essentially what this is telling us. All right, I will end the video there. That was the end of 2.5.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.